Hello, welcome to the third unit, matrix decomposition and pseudo inverse of a matrix. So already you have seen singular value decomposition for module 1 we have seen. Now this is the second module. Okay. So before going to see the problem, so we will summarize what we have learned in the previous video. So what is singular value decomposition? As I said earlier, it is abbreviated as SVD. Suppose A is a m by n matrix, then the singular value decomposition of A is of the form A equals to U sigma V transpose, where U and V are orthogonal matrices. So U is a matrix of order m by m and V is a matrix of order n by n. So sigma we have to choose in such a way that this product is conformable for multiplication. So sigma is m by n matrix, and the principal diagonal entries of the sigma matrix is nothing but they are the singular values of A. And the only caution you have to take is when you are writing sigma, you must list the singular values in the descending order. So we have seen already what is meant by singular values. Okay, so they are the nothing but square roots of eigenvalues of the matrix A transpose A, and you must take it in the descending order. So they are called the singular values. Now we'll see the problem. So in the last video we have seen singular value decomposition for a rectangular matrix where the order is 2 by 3, and here we are going to see another rectangular matrix whose order is 3 by 2. Here in this case it is 3 by 2. So the first step is here, write the SVD form of the matrix A. So the SVD of A is of the form. So what is a matrix A order? It is 3 rows, 2 columns. A is 3 by 2. So M is 3, N is 2. Therefore, your U matrix must be of order M by N. That means 3 by 3. And your V matrix must be of order 2 by 2. And therefore, automatically your sigma must be of order 3 by 2. So first we will compute V matrix, then we will compute sigma, then followed by U. So to compute V matrix, what I require is eigenvalues of A transpose A, eigenvalues of A transpose A, and from that eigenvalues I will calculate the corresponding eigenvectors. Next I will check whether those eigenvectors are orthogonal or not. If they are orthogonal, then I will normalize those vectors and I will construct V by taking those normalized vectors as columns for V. So now we are calculating first V. So for that we require A transpose A. So A transpose means the transpose of this one is written here. A is this given matrix. So this is of order 2 by 3. This is 3 by 2. Therefore the resultant is 2 by 2. So this matrix we will get by multiplying these two. So I am taking this one as B. So first I require the eigenvalues of this, means the eigenvalues of this matrix. So the characteristic equation we are writing here. So which is det B minus lambda equals to 0. So from this 2 minus lambda 1, 1, 2 minus lambda is 0. If you expand this determinant, we will get lambda is 3, 1. So always write the eigenvalues in the descending order. Okay. So here 3 and 1 are the eigenvalues. Now I am going to calculate the eigenvectors corresponding to these eigenvalues. So for that I will consider the system. So what is the system is here? A minus lambda I into x equals to 0. So A minus lambda I is this one into x is 0. So first I will calculate for lambda equals to 3. So put lambda equals to 3 here. If you put lambda equals to 3 here, 2 minus 3 is minus 1. 1, 1, 2 minus 3 is minus 1. So I have to make this as upper triangular means I have to make this entry as 0. So what I am doing is I am adding R2 plus R1. So 1 minus 1, 0, minus 1, 1, 0. So by back substitution, minus x plus y equals to 0. This implies x equals to y. So I am choosing y is k, therefore x is k. Therefore, xy equals to kk. K is outside 1, 1. So I am choosing k is 1. Therefore, the first eigenvector is 1, 1. Similarly, put lambda equals to 1 in the same system. So we will get this one, right? So here we are reducing this into upper triangular matrix by subtracting row 1 from row 2, r2 minus r1. So we'll get this one. So from this, by back substitution, x plus y is 0, x is minus y. I am choosing y is k, therefore x is minus k. So k we are taking outside, which is minus 1, 1, and clearly k is not 0, which is a scalar, right? So if I take k is 1, I will get minus 1, 1. So this is the eigenvector of B corresponding to the eigenvalue lambda equals to 1. So now we got two eigenvectors corresponding to the two eigenvalues. So first we have to check whether they are orthogonal or not. Clearly they are orthogonal. So 1 into minus 1 minus 1, 1 into 1 is plus 1, so which is 0. So they are orthogonal. So x1 and x2 are orthogonal. Once they are orthogonal, normalize those vectors by dividing with its norm. So for x1, the norm is root 2. So if I divide this with root 2, 1 by root 2, 1 by root 2. For x2, its norm is also root 2. So minus 1 by root 2, 1 by root 2. So norm is nothing but square root of component squares. Minus 1 square plus 1 square is root 2. So I have divided this vector with root 2. So we got this one. Minus 1 by root 2, 1 by root 2. Next, calculate the singular values. So the eigenvalues we got is 2. What are those? One is 3, another one is 1. So the singular values of A are sigma 1 is root first eigenvalue, the largest one you have to take. Next largest you have to take as sigma 2. So therefore, what is V? V is constructed with these two columns V1 and V2, and sigma equals to, we have to construct with this singular values. So what is our sigma order here? The sigma order is, if you go back and if you see here, the sigma order in the beginning, the sigma order, if you see, which is 3 by 2, 3 rows, 2 columns. So 3 rows, 2 columns. So first we have to construct 3 rows, 2 columns. So the first principal diagonal entry is root 3. The second principal diagonal entry is 1. Remaining you have to keep it as 0, 0, 0s only. So we got V and sigma. Next we have to compute U. So to compute U, we know the formula. First U1 is 1 by sigma 1 AV1. 1 by sigma 1 means root 3. A is the given matrix. V1 is, we know this is our V1. So if you multiply, you will get this one. U2 is 1 by sigma 2 AV2. Sigma 2 is root 1. Root 1 is 1. So we got the second one. So, but U is a matrix whose order is 3 by 3. So I require one more U3, right? But here if you see, the eigenvalues is not available here. Only two eigenvalues we got. So how to construct U3 means, I have to use the Gram-Schmidt process to construct U3. So we have seen already the Gram-Schmidt process. So using Gram-Schmidt, we can construct U3, which is orthogonal to these two vectors. Okay. So you have to use that process. So using that process, here we calculated U3. Therefore, our U is U1, U2, U3. So we got U. Therefore, U sigma V transpose. U is, just now we got, V is U sigma, this is sigma, and V transpose. So if you multiply this, we are getting the original matrix A. So this is the singular value decomposition. So we have seen two problems. In the module 1 video, we have seen rectangular matrix of order 2 by 3. In this second module, we have seen rectangular matrix of order 3 by 2. So the same it is for any square matrix also. Okay. So now we'll see what is the application of this one. So SVD is very powerful in data compression and image processing. Okay. So what is this? We'll see. So efficient transmission and storage of large quantities of digital data has become a major problem in our technological world. So SVD can be used to compress visual information for the purpose of reducing its required storage space and speeding up its electronic transmission. So in this, the first step in compressing a visual image is to represent it as a numerical matrix from which the visual image can be recovered when needed. Okay, so we will compress this visual image using the numerical matrix. For example, a black and white photograph might be scanned as a rectangular array of pixels and then stored as a matrix A by assigning each pixel a numerical value in accordance with its gray level. If 256 different gray levels are used, so 0 is used for white, 255 is used for black, then the entries in the matrix would be integers between 0 and 255. The image can be recovered from the matrix A by printing or displaying the pixels with their assigned gray levels. So this is the procedure. Okay, so which is one of the applications of singular value decomposition. So this is a simple process. Okay, so I am Srikant Reddy. Thanks for watching. I will see you in the next video.